Deouskar, and this is a session which I'm hosting on the Coanda Effect. It is a quite well-known and quite applied principle in fluid mechanics, and is used in a lot of places from aerospace, aeronautical, to all the way to ocean and naval engineering. So let us begin. And so many of you here are not quite familiar with the aeronautical realm. So here are some basic terms that I'll be using in today's session. So viscosity is basically nothing but uh, Gadhapan, Gadhapan of a liquid, yeah, right? Like you say that honey is more viscous than water, and so on. Water is more viscous than air, and so on. A streamline is the path that a fluid particle inside a flow tends to follow. Yeah, like have you seen those line following robots? They follow a path, and in case of fluid particle, this path is known as a stream. Reynolds number is a dimensionless quantity that is used to determine what type of flow it is. Okay, so there are two types of flows. First is a laminar flow, and second is a turbulent flow. In laminar flow, the streamlines of all particles do not intersect each other. All right, they are neatly arranged. But in turbulent flow, there is a lot of overlapping and there is a lot of chaos. There are some more terminologies that are going to be used in this presentation. If you don't understand, please wait until the doubt session and then you're free to ask. So, yeah, starting off with the topic, the Coanda effect. So I'm pretty sure that everyone has experienced this happening in our lives, right? When we pour one liquid from one container to other, most commonly it's tea or coffee, and then it sticks to the surface. Sticks to the surface, right? Coanda effect basically tells the fluid sticking to a surface. It was given by a Romanian inventor named as Henry Coanda, and this is the scientific definition of this principle. It is a very concise arrangement of the mechanism of the fluid, right? This definition. So the Coanda effect is the tendency of a jet of fluid to follow flat or curved surface and entrain the fluid from the surroundings, so that a region of low pressure develops. So this definition basically defines the entire mechanism. So there is a fluid jet. Okay, in this fluid jet, there are two things happening simultaneously: entrainment and the formation of a low pressure region. Due to this, two things happen which fall under the category of Coanda effect, which is the interaction with the foreign surface, due to which the continuation of adhesion happens. Now, this might sound really complex to you, but I'll go on explaining, and I think it will become much simpler. So, coming on to the first step, that is the fluid jet initiation. So a fluid jet is basically nothing but a fancy way of saying a flow of fluid. Like fluid jet is a flow of fluid, right? It can be from, let's say, if you blow air from your lips, it's a fluid jet. If you water your plant from a garden hose, it's a fluid jet. There the fluid the thrust generated by a turboprop or a turbine engine, it's a fluid jet. So, as I mentioned, there are two types of flows. First is the laminar flow, and second is the turbulent flow, right? So, in laminar flow, the Reynolds number is lesser than 2000, and the Coanda effect is much stronger. That it this would be self-explanatory as I explain the other mechanisms of the Coanda effect. Now, in this fluid jet, there is a factor, there's a phenomenon occurring as entrainment. Okay, entrainment is a process where a fluid drags another fluid or a solid along with it. So the best example of this will be like, let's say when you are when you are using a hair dryer, your hairs they get pushed due to the fluid, right? They get pushed because the fluid it drags your hairs along with its flow, right? It drags your hair. It transfers its momentum to your hairs. So this is what is entrainment of fluid. It also occurs in the case of different fluids. For example, the air, which is a fluid, and the ocean waves, which are fluid. So when the air, there is a wind going, or like wind up upon the surface of the oceans, the wind tends to displace the ocean water. So this is an example of one fluid entraining with another fluid to transfer the momentum. So in this photograph, as you can see here, there is a jet of a fluid. And okay, so this photo explains why entrainment actually occurs. So between the streamlines, due to the ambient pressure is the external pressure. The ambient pressure sorts of pushes the layers of the fluid jet together, right? It pushes the layers of the jet together, which cause them to sort of stick. And this sticking is known as entrainment of a fluid. Now, we can understand this entrainment of, and yeah, so when the ambient pressure pushes the surfaces of the streamline of the fluid, it sticks together. Now since this sticks together, there is a low pressure region that is created, and low pressure region is what you can call a vacuum. So it pulls in more air, more pressure, and more stickiness. So this is what the entrainment cycle of a fluid is. So we could understand that the entrainment for a higher speed jet is more compared to the entrainment done by a low speed jet. This can be easily proved by the Bernoulli's equation. So the Bernoulli's equation, as you all may know, is that pressure plus the total kinetic energy plus the potential energy remains constant in a fluid flow. So, how is this correlating with my previous statement of entrainment that higher speed causes more entrainment and lower speed causes less entrainment? So, according to the Bernoulli's equation, pressure is inversely proportional to the velocity, right? Which means if pressure decreases, the velocity increases. And remember what was being formed before, a low pressure region. So this low pressure region was causing a higher velocity region. Now, how do you explain this inverse relationship from this equation? This is a mathematical proof of the inverse pressure velocity relation. Very easy and very simple. So basically, this is the Bernoulli's equation. Here, K is the constant. And if we consider the flow to be linear, that means the height of all the flow points is the same. This h becomes zero, and this eliminates. So it gives us pressure plus the kinetic energy is equals to constant. If we transfer the kinetic energy over here and then differentiate both sides with respect to v, that is velocity, we get this. And okay, so this would become zero since k is a constant, and half rho will be coming out, negative half rho, and v square would be reduced to 2v. The 2 cancel. We get the rate of change of pressure is equals to the negative of density times velocity. So basically, what this means is that the change in pressure is negative of the change of velocity. That is what it means. All right. When the pressure is increasing, the velocity is decreasing. It's not the conventional inverse relationship in which one is inversely, that is one, like it's not P is directly proportional to 1 by V. It's this kind of relation. It's rate of change is directly proportional to the negative of the variable too. So yeah. Now, okay, so the low pressure region has been formed. Now what? So low pressure region is formed because let us introduce a plane surface. All right, let us introduce a plane surface in the flow. Now, due to entrainment, all the fluid streamlines will be sticking together, and the ambient pressure, the pressure by the atmosphere, would cause it to go down. This entire thing, this entire blue lines, it would cause them to bend, and continue along the surface, right? Because there is a low pressure region being formed there. Simply, this region is low pressure, and this is the ambient pressure. Ambient pressure is always greater than low pressure because it's atmospheric pressure. Now, as I mentioned, it tends to go and stick to the surface. So this is in the case of straight plane. Now, the Coanda effect occurs more in curved surfaces. Why? Because in curved surfaces, the velocity of the fluid uh, is continuing to go higher as the fluid propagates through the curve. And as I mentioned, higher velocity means lower pressure. And the more low the pressure is, the more the difference of the pressure is. And the more the difference of the pressure is, the more is the effect of the ambient pressure. So it causes the fluid jet to like sort of stick to the surface. Now, this is what basically the Coanda effect is. Now, this is a computational fluid dynamics simulation run by ANSYS Wind that depicts the Coanda effect. So, as you can see here, this is a curved surface, and this hole over here is the fluid jet. And as you can see here, it is continuing. It's sticking to this curve. It's sticking to this curve, and this sticking to this curve is basically the Coanda effect. Also, in this image, there is the nozzle, and as you can see here, it's continuing to stick to the surface. And here also in this plane region, there is something happening known as Coanda vertice. I'll tell you about it later. So now let's come to our conventional example and try to explain it with the Coanda effect. So you pour one liquid, you pour one fluid, and due to the ambient pressure, that is the pressure exerted by the atmosphere, it tends to stick. And also, firstly, this entire thing remains entrained because, as I mentioned, entrainment of a fluid is applicable not only for gases, not only for liquids. It's like for every sort of fluid in existence. That is the entrainment. But it is more commonly found in liquids. It's more prominent in liquids because of their surface tension, which is higher than that of gases. So the entrainment is more common. Now think of the best example is when you are watering the plants using the garden pipe. The entire water the fluid that flows comes out to be in a line, right? Comes out to be a line, and that is solely because of entrainment. So entrainment happens, and there is a low pressure region being formed over here. To be honest, this is a no pressure region because there is this, cup. There is no fluid below the fluid. So yeah, and also there is ambient pressure, which forces which acts onto the entrained flow, causing it to stick to the surface of the cup, and hence this happens. Annoying thing, I know. Now, yeah, now coming on to the formation of low pressure vortex. In higher velocities or in some flow conditions, especially in aeronautical applications and when the speed is very high, there is a low pressure vortex that is formed. Okay, low pressure vortex means there is a vertex, and a vertex is like a circular motion of the fluid particles across one center. What this happens, this acts like an even stronger vacuum, pulling more particles in the flow, right? More particles in the flow, and hence causing more suction, and hence causing more vacuum, and hence even more deviation, even more sticking. So these are some effects of the Coanda vortices. They stabilize and destabilize the airflow depending upon the position and strength. This means you can use them positively in aeronautical engineering applications, right? They also it's used to mix two different fluids in jet exhaust, combustion chambers, and all. And yeah, as I mentioned, low pressure zone even causes more surrounding air of fluid to get into the flow and stick to the surface, increasing the entrainment. And we could also manipulate if we are able to employ effective techniques, then we will be able to manipulate the Coanda vortices and control the direction of thrust and increase lift without mechanical deflection. So this is a bit complex part. That is the mathematical modeling of the Coanda effect. So the pressure experience a drop across the curvature of the surface. The pressure tends to go little bit less across the surface. Now less mathematically is operated by a gradient. So this equation it distributes the pressure, the rate of change of pressure. The LHS is the rate of change of pressure across the arc length of the curvature, that is S, and here it is the change in velocity across the arc length, and this entire thing from the Bernoulli's equation that we derived earlier. is minus rho v dvds. So after getting the gradient, if we calculate the centrifugal force, which is the downforce acting, and the centrifugal force is the result of pressure difference, and hence it causes the thrust generated, or there is the force generated by the Coanda effect. So this is going to be a very generalized model, nothing complicated. For ease of access of understanding, there are more complicated models that are used, but I'll just stick with the simplest one. So force is equals to now we all know pressure is force upon area. Okay, so this can be rewritten as force is there. Now here is the rate of change of pressure. Now this is actually the gradient that we calculated previously. And after substituting this into the area of the curved surface, we could somewhat approximate the force that is being generated due to the quantum. If you want to get really accurate, then there is this Navier-Stokes equation, which is a partial differential equation. This symbol here, it's a partial differentiation. Very complicated. I would not go into the like I would not go into the depth of this equation, but I would just explain you what it is. But yeah, so this here is the pressure gradient that we calculated before. This here actually is a better representation of rho, the viscosity that we took, right? It's a better representation of it. And similarly, this here, it is like it calculates this across the vector field. It's really complicated. You won't understand it, but yes, it is used for higher and more accurate modeling of quantum effects. Okay, guys, enough mathematics. Let's get to some interesting stuff. And yeah, this is the application of the quantum. So I think you guys might be knowing an airfoil. If not, I'll be explaining it. An airfoil, okay, so you take a wing of an aircraft, okay, and you slice it apart. The shape that you will get, or the cross section of the wing, is known as airfoil. Airfoil is a shape. This shape, as you can see here, this is an airfoil. How does this airfoil or this shape generate lift? Okay, so this is a curvature. So as the fluid like comes in contact, it gets accelerated here, accelerated and exerts a down force, right? It sticks to the surface of the airfoil. It sticks to the surface. That is what the Coanda effect is, and exerts down force, right? Down force, and this down force pushes the aircraft upwards, because here there is no Coanda effect happening, because as you can see here, almost this it's almost straight and this is curved. So it comes and exerts a downforce in this direction, and this and causes an extra force to be applied, and thus it causing lift. Okay. Now also we could understand the principle of stall. You know, like stall. A stall is the condition when the wing is not able to generate enough lift to keep the aircraft in air. Okay. So, or you could say that the drag is more than the lift. You could say that actually its coefficient of drag is more than the coefficient of lift. But yeah, somewhat you can say that. Now, angle of attack. AOA is the angle of attack. Angle of attack is the tilt that you put in the airfoil. Is the tilt that you put in the wing. Just you can see that this is lower angle of attack. This is higher. This is somewhat medium angle of attack, and this is higher angle of attack. So basically, the more accurate definition of angle of attack is that it is the angle that is formed between the chord line of the wing with respect to the direction of the fluid flow. But it's complicated. You might not know what a chord line is. So just think of it as the tilt in the wing. So here, as you can see here, there is less AOA, or so their Coanda effect is more prominent because the entire surface, the upper surface of the wing, is coming in contact with the air and is undergoing the acceleration due to the Coanda effect. Similarly, in this case is almost the same. But in this, as you can see here, the separation is more. Like there is a flow separation. These circles, as you can see here, these are known as cavitation, or you could say flow separation regions. Now, due to this flow separation regions, there is the loss of effective weight, effective lift, and there is the stall. Also, you might ask me that when we tilt the aircraft wing upwards, right, the aircraft tends to go upwards. So why is that? Why that is completely because in this case, the Coanda effect would be more because some part of this lower surface will be coming in contact with the upstream of the wing, upstream fluid flow, due to which there would be, as I mentioned, more Coanda effect and more entrainment and more lift. But if you tilt it too much, then there would be absolutely chaotic menace, and that would be this, where it would be separating because of, you could think of it as drag. There is a tendency, there is a limit for the Coanda effect, there is a limit for the curvature, and that limit is completely dependent on the velocity, right? You could achieve Coanda effect on extremely curved surfaces as well, but for that you'll have to have a higher velocity. And that is the exact reason why fighter jets tend to stall less compared to commercial aircrafts or beach aircrafts, right? Because their velocity is higher, and hence they are able to hence they are able to resist stall more compared to commercial airlines. So that was it. I hope you guys understood the presentation and like the lecture. And I think it clearly defined how a lift is generated by an aircraft wing or an airfoil. If there are any questions, then you can ask, although the time is less, but yeah, I'll try to answer. Any questions? You
Uh,
can,
can you can you explain like how lift actually takes place on instance of the quantity? Uh,
you
that's
want
it.
to understand lift, how lift happens.
Yep.
Yeah. So basically, lift happens. Okay. So lift happens when there is a pressure difference. You see this airfoil, right? You see this airfoil. There is a pressure difference that happens. This part is called upper surface. This part is called the lower surface. On the upper surface, all right, there is a low pressure region, and on the lower surface, there is a high pressure region. So high pressure pushes the wing upwards, right? Pressure is more, so it will push it upwards, and it will cause lift. You could also apply the Coanda effect. As I mentioned, where there is Coanda effect, there is low pressure region. So the upper surface undergoes Coanda effect, so there is low pressure region. And the lower surface undergoes no Coanda effect, it go undergoes ambient pressure, so there is high pressure region, so it causes lift. Uh, there are two explanations of generation of lift. First is by Bernoulli's theorem, and the second is by this Coanda effect in Newton's second law of motion. But for the Bernoulli's theorem, I think that might be more complex for you.